All right, so the talk that I'm going to give is not the one I originally envisioned presenting. When I first received the invitation, I thought, okay, well, I'll tell them about all the cool magnospheric science that we've done over the years, and it will be a lecture. It will be a science lecture, because that's what scientists do. But Laura indicated that she thought that the talk should be more autobiographical, and so I revised the talk, and it is going to be more about journeys, about my journeys. And I have to apologize right up front for all of the I and me words that you're going to hear in this presentation. Scientists generally don't talk about themselves very much. They prefer to talk about the science that they're learning. So it's a little bit different than the talk that I would have given originally. So I'm going to talk about those journeys. I'm going to talk about where the journey started, some aspects of my higher education life, college and graduate school, some of the aspects of the early years when I was first at Los Alamos National Laboratory, and then the later programs. I'll tell you a little bit about my current activities, and then I would like to return to some lessons learned, some sort of sum it up over the career kind of lessons. So first, this is a talk about journeys. They're about the physical journeys that I have taken, the various places that I have lived, the various institutions that I have worked for. You see that here, these black arrows sort of take you on my physical journey. It's also about the virtual journeys that I've had, the visits to the various planetary bodies in the solar system that I have studied over the course of my career. And so these are the virtual journeys, these red arrows. Scientific journeys, I'm going to tell you a little bit about some of the science that we did as we studied these various bodies. And then you will also hear about my personal journey. So first of all, I was born in a small town on the eastern plains of the state of Colorado in the U.S. My father was a school teacher. My mother was a war bride, a French war bride. She did not work outside the home, but she was very engaged with community service activities, very busy and very productive. When I was 4, we moved to the capital city of Denver, and that's where I basically grew up, was in Denver. I'm going back this far to just to point out to you that my childhood was perfectly normal. I was just an ordinary kid, an ordinary family. There was nothing in my family background that would predispose me to a career in science or even to an interest in science. So it was just a normal kind of childhood. I did well in school. I enjoyed doing well in school, and that was about it for my childhood. Okay, when I went to high school, I continued to do well in school. I enjoyed math and science courses, probably because that I generally did very, very well in them. But I found that the most formative class I took in high school was English. And this was for a couple of reasons. This is my English teacher from high school. He was he had very high standards, and he had high expectations of his students. And we wrote a lot, and when he graded our papers, he graded them rigorously. If you had one run-on sentence, one sentence fragment, or 3 spelling errors, you had an automatic F. So he was very strict, and so we learned to be attentive to the details of our writing. I think that served me very well later on in my career, so that was a very useful thing. He also cured me of the habit of using commas indiscriminately. That was a good thing too. The second aspect of that class that I think was really very formative, very important, was when we would be discussing the literature that we were studying, we would sit in a circle. The students would sit in a circle, and Mr. Lee would pull a student chair into the circle. He would become part of the circle, and he would begin the discussion by making some fairly provocative statement about the literature we were discussing, and then he would challenge us to nail him to the wall. And we would proceed to try to do so. And that meant we were supposed to critique what he had just said on the basis of evidence that was in the literature we were studying. So it was critical thinking that he was teaching us, and it was really very important, and he rejoiced in being nailed to the wall. He was secure enough that he welcomed well-reasoned arguments counter to what he had said. And I think that was a great gift to his students, to teach us how to think critically and how to communicate in that objective, critical, evidence-based way. And that, I think, was a skill that has definitely come to be useful in the world of science. After high school, I went to a small college, not too far away, but academically quite rich, Colorado College. This is where I learned to love physics. And part of the reason was I had originally intended to go into chemistry as my major, but had to take physics as a prerequisite. And I discovered early on that the physics laboratories smelled very much better than the chemistry laboratories. So, okay, physics is a good thing to study. So that was part of it. The other part of it was this gentleman here, Richard Hilt. He became my advisor over the course of my time there. He had a great love for physics, and it was very infectious. He had an enthusiasm for the subject. He taught my junior level, that's the third year in college. He taught an advanced mechanics class, classical mechanics class, out of a book that had some very difficult problems in it. And he would assign these problems, and the class would go away and try to solve them. And then each Wednesday night we would have a problem-solving session in the evening. And he always challenged himself to solve the problems as well, independently. He didn't just look up his earlier solutions. He would actually try to solve them himself. And it became kind of a contest of who amongst us could solve the problem. And I think he was as happy when one of us solved the problem that he couldn't do, which was quite rare, but he was as happy under those circumstances as in the reverse. So again, there was this a lack of ego. He was secure enough in his own, in who he was and his own understanding, that he could rejoice in our accomplishments. My senior year, my last year at college, for the fall semester, I did an off-campus program at the Argonne National Laboratory outside of Chicago. This was my first exposure to real-world research. I helped run nuclear physics calculations that they were doing in support of the experiments they were doing with their tandem Van de Graaff accelerator at Argonne. And there was also a strong independent study component to the studies that semester, and I think that's very familiar to people in the British educational system, is that independent study. But it was also very useful for me to get that experience of how to track things down on my own. And the other real benefit of that semester off campus was I met my future husband, who's here today. So after graduation, I started my graduate studies at the University of Minnesota in Minneapolis, Minnesota. My husband-to-be was still a student in St. Olaf College in Northville, Minnesota, so there was some attraction to the Great North for me. And then after he graduated and was admitted to medical school at the University of Iowa, I transferred to the University of Iowa. Iowa at that time, as now, was a real powerhouse in space physics. The chairman of the department was James Van Allen, who was famous for having discovered the radiation belts that bear his name. This was the cover of Time magazine. That's quite a prestigious recognition to be on the cover of Time magazine. And he was fortuitously on my interview committee when I first started in the department. And he said he had he thought it would be a good idea if, along with the coursework that I had to take, if I got started on some small research project, and he just happened to have a whole notebook full of small research projects that I could consider doing. So I took him up on that, and I worked on that little project turned into my master's thesis, which in the end was to look at data from the Pioneer 10 spacecraft as it was traveling outward past Mars through the asteroid belts out towards Jupiter. Pioneer 10 was the first spacecraft to go past go through the asteroid belt and to encounter the planet Jupiter. So my master's thesis was a study of cosmic ray intensities along this path from the Earth to Jupiter. And then that gave, once Pioneer 10 got to Jupiter, that gave way to my PhD research, which involved the study of the energetic charged particles that are trapped in Jupiter's magnetosphere. Now, a magnetosphere, for those of you who aren't as familiar with that, is the region of space around a planet that has an intrinsic magnetic field like the Earth. The Earth is like a big dipole magnet. And other planets are that way as well. Jupiter, notably, has a very strong intrinsic magnetic field. And the region around the planet that's dominated by that magnetic field, as opposed to the magnetic field that is embedded in the solar wind that's coming out from the sun, is known as the magnetosphere. And the properties of charged particles and magnetic fields are such that there's kind of a barrier that the magnetosphere is kind of a region which excludes the solar wind and traps material charged particles within it. So it forms a large obstacle in the solar wind. The solar wind is blowing out from the sun. It's supersonic at this distance. And so there's a bow shock that's formed in front of it to slow and deflect the solar wind flow around the magnetosphere. But this region in here that's dominated by the magnetic field of the planet is known as the magnetosphere. And in this region, you can have charged particles that are trapped like in a bottle, in a magnetic bottle. They're trapped on these magnetic field lines. And there are a lot of really interesting processes that go on in a magnetosphere that can accelerate those particles up to very high energies, millions of electron volts. And that's basically what the instrument is that we were using, that we were flying on Pioneer 10, was to measure these very high energy charged particles in Jupiter's magnetosphere. And this shows you the first intimations that magnetosphere was there. This was Pioneer 10's inbound trajectory in towards Saturn. These are count rates from the various detectors. They were Geiger tubes, is what they were. Various energetic charged particle detectors. And as we approached Saturn, we crossed that bow shock here, and then we entered into the magnetosphere here, into this across the purple line at the magnetopause. And then you can see over the course of several days, those count rates just continued to progressively get higher and higher and higher. The closest approach was really over here, and they went very much higher in that region. But this, for days, the spacecraft was passing through this outer region of the magnetosphere. It's a huge thing. If you could look at the Jupiter's magnetosphere on the night sky, even at this distance, which is like 4 astronomical units at closest approach, it would be this size, the angular diameter, compared to the moon. So if you could see the magnetosphere of Jupiter, if it were somehow illuminated, it would be way bigger than the moon. Okay, so that was pretty exciting. My thesis had to do with the fact that the charged particles that were trapped in the magnetosphere execute a drift around the planet. Their motion is basically an azimuthal drift. But as they drift around the planet, when they encounter one of the moons of Jupiter that are deep inside the magnetosphere, they get absorbed. An energetic charged particle will run into the moon, and that's the end of it. And so, in the direction of the electron drift, or the energetic particle drift, you get a shadow behind the moon. and that gradually fills in through diffusive processes. And so when you are coming toward the planet, when you cross the orbit of one of those satellites, one of those moons, you'll see a dip in the count rates of these energetic charged particle detectors, which is because that moon has been depleting the population in that region. And so if you can study these dips and how they fill in with time, you get an idea of what the transport processes are that move those charged particles back and forth radially. So that was the subject for my thesis. But what we noticed, this was data actually from Pioneer 11, which followed Pioneer 10 by a year. What we noticed is that the behavior of the proton population was quite different than the behavior of the populations of the electrons. And so there was something different happening with the protons. And part of my thesis was to try to identify why the protons had such a different profile than the electrons. And what we came up with was that these very strong proton losses observed at Io's orbit were due not just to the satellite absorption that I've talked about, but to plasma processes that were causing the material to interact perhaps with neutral material that was present or with a dense low-energy plasma and be scattered out of the magnetosphere into the atmosphere of Jupiter. That turned out to be actually correct, and subsequent analyses with Voyager data and again with Galileo data confirmed that this process was an important process in the region around Io. And we came to learn with Voyager that that was because Io itself is putting out lots of gas, sulfur. It's got volcanoes, and those volcanoes spew out neutral gas that gets ionized, that participates in these interactions that can cause strong losses of the protons. Well, this work was done under the guidance of Dr. Van Allen and by a visiting professor from Germany named Chris Gertz. This was a very productive arrangement. Dr. Van Allen was really an expert with the data analysis, and Chris Gertz was very good with the theory, so it was a very productive arrangement. It didn't have a very happy ending. Chris was one of the people who was murdered in one of the early campus violence examples in the U.S. Just a few years after I left Iowa. So that cut short a really very productive career, and that was a very sad thing personally and professionally. But one other good thing that did happen during this time interval was that I finally caught him. All right. Okay, so after I received my PhD, my husband was doing his residency in dermatology at the University of Iowa, so I stayed on and did a postdoc, again working with Dr. Van Allen. And now, by this time, Pioneer 11 had passed by Jupiter. I'd gotten my PhD dissertation out of that, and it was on its way to encounter Saturn. So this, in order to get the data from the Saturn encounter, we all had to traipse out to Mountain View, California, to Ames Research Center, where we would take our data points every 15 minutes. We would plot our data points by hand to see what was going on at Saturn. This is a picture of the workroom at that Pioneer 11 encounter with Saturn. And the reason I really like this picture is it shows Dr. Van Allen here listening attentively to, yes, that's me with all that hair, to a mere postdoc. And that was a characteristic that he had that I greatly appreciated. He was respectful and kind to everyone he knew, from the highest muckety-mucks to his graduate students, to his undergraduate students. He treated everyone with respect. He listened to what you had to say. If he disagreed with you, he disagreed in a kindly fashion. He never put anyone down. And I think that was very inspiring, and it really helped our self-esteem to know that he might disagree with it, but he wasn't going to just ridicule us because of it. So that was a really wonderful aspect of his personality. Okay, so at Saturn, the same sort of deal happened. There were these absorption signatures from the moons, and particularly the moon Mimas, where when you would pass through the orbit of Mimas, there would be a depletion in the count rates for these energetic charged particles, and so the same kind of studies could be done. But really interesting, if you looked in detail within these what we call macro signatures of the satellite absorption, there were places where there would be this tiny little dip that would correspond actually to a direct crossing of that shadow, not too far from the moon itself. And so this was the direct downstream shadow, which was called a microsignature then, to distinguish it from the broader region affected by the moon. And by looking at these signatures, we could get a very good idea of how rapidly they fill in, because we know when the moon used to be there, and so we know how long it had taken to get to that level of refilling in that shadow. So that provided a really good opportunity for looking at the transport, the radial transport at Saturn, and that technique has been used to great effect by subsequent observers, both with the Voyager spacecraft and more recently with the Cassini spacecraft at Saturn. And another little microsignature entered my life at this time. This is our son Davis, born in 1979. Okay, so after the postdoc at Iowa, we went for a 6-month postdoc at Max Planck Institute for Aeronomy in Lindau, West Germany. That was maybe not the scientifically most productive phase of my life, but I think it was really valuable for me because I got to meet a lot of European investigators, a lot of people that I would later encounter in other circumstances, and it was really good to already have established a relationship. I got a chance also to understand more how other places do science. It was different, very different culture in Germany than it was I was used to at Iowa. So I think it's a really valuable thing, even if you have a wonderful situation in your home institution. It's a really valuable thing to get out to see how other institutions, what the cultures are in other places, how research is done elsewhere. And I continued working on Saturn there. And then, yay, a permanent job. I was offered a staff position at Los Alamos National Laboratory. So we took ourselves to Los Alamos, New Mexico, to Los Alamos National Laboratory. And there, the group that I was working with was pursuing questions of Earth's magnetosphere and its interaction with the solar wind. So I not only came back closer to home physically, but I was closer to home virtually now studying the Earth. So when I first arrived there, that group was busily examining data from the International Sun-Earth Explorer, a series of satellites which had just recently been launched. That was the ICE mission. This mission consisted of 2 spacecraft that were co-orbiting fairly closely in the same orbit, so that you could distinguish spatial and temporal variations, which is always a problem with a single spacecraft measurement. And then there was a 3rd spacecraft, the IC3, which orbited the Lagrangian point between the Earth and the Sun. It's about 200 Earth radii towards the Sun. It's a semi-stable point gravitationally, and the satellite can orbit there and serve as a monitor of the solar wind that was coming towards the Earth, while the other 2 IC spacecraft were examining the effects on the magnetosphere. Our emphasis with the IC data was primarily on this region, the bow shock, and the region upstream from the bow shock, which, because the plasma here is very diffuse, it's very tenuous, you actually don't have collisional, you have very few collisions. And so energetic particles can actually leak back upstream along the magnetic field lines from the interactions that are going on at the bow shock. But those were the areas of particular interest for IC, at least our part of IC. we flew for the first time plasma analyzers that have very high time resolution, and so we were able to resolve the bow shock itself. These were the colleagues that I worked most closely with at Los Alamos. Peter Gary, a theorist, he was actually the one who hired me. I learned after coming to work with him and doing theory for a year, I learned really that my heart was in data. And so I kind of migrated more into the data analysis side of things, and that's pretty much how I've always been ever since. Is I'm really turned on by the actual measurements. They're telling you what's going on in the place that you're looking at. So Bill Feldman is an idea a minute kind of guy. He's got incredible enthusiasm. Is very infectious. He's just a really just full of ideas and gets things moving. Jack Gosling, I would say, is probably one of the best scientists that I have ever known. He is a scientist. He has an excellent knack for going after the essence of what the problem is. Just a terrific guy. And I want to say a little bit more about Jack here. So Jack has received many awards over the years. He's received the National Academy of Science Arkatowski, I think that's how it's pronounced, award. He's the John Adam Fleming Award from the American Geophysical Union. So he is definitely a well-recognized scientist in our field. He and I collaborated closely for about 12 and a half years. And during that time, we co-authored 67 papers together. This particular picture was taken when he was receiving, I think it was when he was being invested as a fellow of the American Geophysical Union. And to show how well we cleaned up, he posted this picture outside the area between our two offices. And a local wag cut off the heads and exchanged them. And all I could say was, I look way better in a suit than Jack looks in a dress. So Jack had the so what is his favorite question. He always would zero in on that. It was really important for him to identify what the significance of what you were doing was, why anybody would care about it. And, I came to understand that question is probably the most important question that we as scientists or we as researchers or anyone can ask is, so what? What's the point? Why are we studying this? Why do we care? So I thank him for that. So IC made pioneering findings on the structure, dynamics, and consequences of collisionless shocks in plasmas. On the strength of these observations, we overturned the reigning paradigm that plasma instabilities were the primary means of energy dissipation at collisionless shocks. That was a really important step forward. And I like to think this was a really golden time. It was a time when numerical simulations had finally reached a stage of speed and complexity that they could be addressing really realistic problems. And between our colleagues at Los Alamos who did numerical simulations of shocks in plasmas and our measurements from the IC spacecraft and our conceptual ideas about what was going on, we had a very productive combination that led to a great increase in our understanding of how collisionless shocks work. So this is kind of the poster child for how science should work between the observations, the theory, and the conceptual understanding. And a not shocking experiment was the birth of our daughter in this time frame. All right. So after the IC program ended, I briefly was involved in studies of comets. The IC-3 spacecraft, which I told you about, had been orbiting the Lagrangian point upstream from the Earth, was redirected. And I have to say the orbital dynamics people in NASA are really quite amazing, and other space agencies as well. But how they could just take these spacecraft and make them go where they wanted them to go. So what they did was they deflected it out of its orbit around the Lagrangian point, put it into Earth orbit, a long looping orbit around the Earth, and then eventually ejected it and sent it out of Earth orbit to encounter comet Giacobini-Zinner in September of 1985. That pass was through the tail of Giacobini-Zinner. The spacecraft was renamed ICE, International Cometary Explorer, and that actually was the first spacecraft encounter with a comet. 1985, it was 6 months before the whole flotilla of spacecraft arrived to visit Comet Halley. Giotto was the European spacecraft, and there was a Japanese one and a Russian one as well. And that was 6 months after ICE encountered Giacobini-Zinner. So then we also had involvement with the plasma instrument on Giotto, and so I was involved in the analysis of the plasma measurements from Comet Halley as well. And that was actually a dayside passage, a passage through the dayside coma. That was very interesting. So the combination of these two were very interesting encounters with comets. And I learned some interesting physics that has served me very well in recent years in my studies at Saturn. So at Los Alamos, the second major phase of my career at Los Alamos involved plasma measurements that were made on satellites that Los Alamos was flying in geosynchronous orbit. Now, geosynchronous orbit is the orbit around the Earth with an orbital period of 24 hours. So a spacecraft in that orbit stays over the same point on the surface of the Earth. It goes around in 24 hours, the Earth turns in 24 hours, it always stays over the same point. That makes geosynchronous orbit a really important orbit for communication satellites, weather satellites, spy satellites, what have you. There are a lot of satellites in geosynchronous orbit, and Los Alamos National Laboratory fielded, as it turns out, 8 in the end. And those satellites were operating simultaneously for many of those years. So there are years where we have 6 operating satellites at different places in geosynchronous orbit at the same time. That was a very, very rich data set. Geosynchronous orbit is not only a real important one for technological purposes, but it's also right kind of at the interface between the inner magnetosphere, which is dominated by the dipole, the Earth's magnetic dipole. That's where the radiation belts are, is in that inner region, and the outer magnetosphere, in which the magnetic field is significantly distorted by electrical currents that flow in the plasmas that are trapped themselves. And so there's a lot of plasma physical processes that are important in that outer magnetospheric region, and geosynchronous is right in between them and could watch both of them. So we made some important discoveries with these observations about the origins and transport of magnetospheric plasma, both material that was captured from the solar wind and material that flowed out of the Earth's upper atmosphere. It was a really rich data set, as I say. During this time, the 1980s and 90s, there was a turning point in my own career when I began to mentor postdocs and students of my own. And I would say that this was one of the funnest aspects of my life as a scientist, was interacting with these young people who were bright, enthusiastic. They got what the problem was. They came up with creative ideas. It was really a wonderful time, and these folks have almost all gone on to very productive careers, in most of them in the field, others in different fields, but they're very successful researchers in their own right. I think this was my first postdoc, Steve Fuselier. I think he just recently received a very prestigious award from the European Geophysical Union. So I had postdocs from England, from France, from Germany, from Taiwan, and then a few American ringers thrown in. Oh yeah, Denmark, a few American ringers thrown in there. Okay, so the third phase of my research life at Los Alamos has been involved in analysis of data from the Cassini spacecraft to Saturn. So this was my opportunity to return to the physics of Saturn's magnetosphere, this time using data from a much lower energy instrument. Instead of looking at the radiation belts, I've been looking at the sources, the transport, and the loss of the thermal plasma itself, the bulk of what makes up the magnetosphere. Looking at the dynamics of the magnetosphere, all the different processes that are going on there to heat the material, to how it interacts with the solar wind, just a whole host of really interesting problems to work on. That's what I'm here working with Katrina on for these 2 weeks. Cassini has been a fantastic mission. It's due to re-enter Saturn's atmosphere later this year in September, but we have a fantastic data set from a great spacecraft, a great instrument. It's been just a wonderful ride. So, currently, as you heard, I am a senior scientist at the Planetary Science Institute in Tucson, Arizona. This was kind of a virtual move for me in that about half the scientific staff at PSI work off-site. So they have scientific researchers in Switzerland, in South Africa, in India, all around the world, Hawaii. And so it was a very easy thing to for me to work from Los Alamos. I didn't have to move. I retired from the laboratory, but I didn't have to move. And then the laboratory appointed me as a visiting scientist, so I have an office there, and I have access to laboratory resources. It's been a really good arrangement. My funding comes through Planetary Science Institute at lower overhead than the laboratory, so that's been a really good move. And I am mostly personally working on Cassini still. I do continued studies of the Earth's magnetosphere using the geosynchronous data. I have been involved in radiation belt storm probe analysis at Los Alamos. Both of those are kind of on an, I'm looking over people's shoulder for those studies now. I'm not really doing it myself anymore. So I'm kind of in the position of just delivering wise observations. Also, I have an unofficial relationship with the Juno Jade team. So Juno is a spacecraft that just recently went into orbit around Jupiter. So I'm back to Jupiter. I've come full circle. It's really nice. This is an orbit that is polar orbit, so it's designed to really study the aurora at Jupiter. So that's really a very exciting benefit, sort of a dessert for my career. It's really been very fun to do that. And I'm involved with other colleagues at Los Alamos and elsewhere in developing a proposal for a mid-sized Explorer mission, which we hope will be accepted next year. So I want to briefly, before I end, come back to the question of what lessons I've learned over the years. First of all, I want to take a look at what I think the key factors underlying a rewarding career are, at least from my perspective, have been. In this setting, it is important to address the question of whether or not gender was an issue along the way, and then my wise words of wisdom for you. So, lessons learned, the key factors for a rewarding career. I would say it's extremely important to have a supporting spouse, supportive I should say, not supporting, a supportive spouse, or if not a spouse, some kind of support structure. People cannot do these kinds of demanding jobs alone. You need a support structure to help you out in the times when you've got too many deadlines and a sick kid, or you need help sometimes. So having some kind of support structure is a really important part of making your way through your career. Stable childcare. If you have children, stable childcare is really important to transfer these things into mature, competent, capable, pleasant adults. Mentors. I've touched on those as I went along. You could probably see that was going to be one of the themes for the talk. Mentors are really important because they not only teach you, but they promote you. They not only show you how to do it, but they give you the opportunities by introducing you to other people, by putting you forward for recognition, those sorts of things. Mentors are a really important part of having a rewarding career. Enlightened employers. So I worked for the University of Iowa. I was able to work part-time when our son was born so that I could continue my research, my career, and at the same time deal with the demands of a new child. Similarly at Los Alamos, there was flexibility there in the employment situation. I could take time off. I only took a month off to have each of those kids. So the second month was really bad. But there was the opportunity to work part-time so that I could do that balance. And I think that's a really important enlightened way for employers to help make people able to balance their personal lives and their professional lives. And then this arrangement with Planetary Science Institute, it's a really great science institute. I just love this place. But it's also similarly extremely flexible, even as to where you are and when you're working and things like that. So I think enlightened employers is a really important part of career development. And I wish they were all that way. And then I think finally, outstanding, collaborative, and supportive colleagues are really key. These are people that you work with, who you bounce your ideas off of, who feed you mentally. They're people who will advance your career as well by nominating you for recognitions, by getting you onto committees where you can, get more recognition community-wide. So I think this was really, it's important not just for the development of the science, but for the development of your career as well, that you have really supportive colleagues. Okay, so the question, gender, was it an issue? Well, when Laura invited me to give this talk, I said, well, I just never really have experienced any kind of gender discrimination. I just was so clueless right from the beginning. I never knew that girls were not supposed to like math or science. I never knew they weren't supposed to be good at it. I don't know. I was a spacey scientist right from the beginning. That, I think, was a great blessing for me because I didn't have to wrestle with those issues. I just did it. There were, when I think about it, there were maybe 5 times where gender was a factor, where I perceived gender as being a factor in what was in my life. One, on that off-campus program at Oregon, there was a professor who told me, "Oh, you're too cute to be a physicist." I thought that was creepy, and I avoided him for the rest of the time. Early in my career, 2 colleagues made passes at me. That was awkward, and it strained our relationship from then on. But, I think I learned from that. I learned to look at what signals I might be giving people, and I think looking at your own, how you interact with people, it's good to look back at how you're acting as well as how they're acting. At Los Alamos in the 90s, There was an effort to equalize the gender inequality in the pay, and I got a really nice midterm raise. That was, okay, that's very good. I also was recruited to be the director of the Los Alamos IGPP, Institute for Geophysics and Planetary Physics, and the person who recruited me said, we need some female applicants. I did not apply. And then I served on an AGU selection committee for AGU fellows one time, and there was a female nomination, and a member of the committee was really pushing that nomination because we needed more women to be fellows. Okay, those last two, well, the third one's definitely a plus. Those last two seem like their progress in, as we're moving along this path towards what I like to think will ultimately be gender blindness in our field. And so they seem to be making progress along the way, but I think there's a real downside to that comes here that we need to be aware of, is that in that effort to level the playing field, to show preference for females, we do damage to young women's self-esteem by making them wonder if they've received this award because they're a woman, because they needed more women, or if they've been hired because they needed more women. I think that does some damage to women, and I would hope that in the future, all the preferences that are shown now in many circumstances will become a thing of the past, and people will be judged on the basis of their capabilities, their accomplishments, what they bring to the table, rather than quotas that need to be met. But my basic advice to you, young scientists and engineers and everybody else, to resist gender bias where it exists, but don't obsess with it, rise above it to pursue your passion. And the best advice I can give you was actually given by Nobel laureate Richard Feynman. If you have any talent or any occupation that delights you, do it, and do it to the hilt. Don't ask why or what difficulties you may get into. And I would just add, it may take you to some amazing places. Thank you.